All right, so this video we're going to do some example problems for waves and oscillations. Obviously we're trying to make our way through optics, and optics deals with light, and light, of course, one of the ways it can be described is through the use of waves. There's a lot of properties that light has that are wave-like. Not everything. In fact, as you delve into more and more modern physics, we start to uncover the fact that light, although much of its properties are that of waves, sometimes they have particle-like properties, and that is where quantum mechanics comes into play to try to describe light in a more realistic way. And unfortunately, waves just doesn't cut it. However, for a lot of what we want to do for our purposes, the wave nature of light is what's most important. And so we want to describe waves. We want to see how do waves work, what are some of the characteristics that are important. And that way, when we talk about optics, we have some good background foundation to help us discuss the topic a little bit more thoroughly. So we discussed in the previous lecture that waves can be either transverse or longitudinal. And these two different types of waves are described by how the oscillation part of the wave, the part of the wave that goes up and down, the wavy part, in which direction that waviness occurs relative to the direction of the motion of the wave. So for instance, transverse waves are those that when you draw them, they're drawn like this, where the wave is moving this way, let's say, and you have the up and downness, the waviness of the wave, perpendicular to the motion of the wave. So, water waves are like this. Light is like this. The wave moves, let's say, horizontally, but it oscillates vertically. And so, generally speaking, when one imagines a wave, this is what you imagine, a transverse wave. And this is light. One of the transverse waves examples is light, and so this is the important one for us. Longitudinal, however, is the opposite. This is where the waviness of the waviness of the wave, its oscillations actually occur in the same direction as the motion, and this is sound. It's much harder to draw, but imagine air molecules, and as this wave, pressure wave, let's say, travels horizontally, the air molecules that are disturbed get disturbed in kind of a pattern where you have dense amounts of molecules and then rarefied molecules, and then they come together again, really close again. And you could see the waviness. They're moving, these molecules are moving back and forward this way, and so they kind of clump up here, and clump up here, and clump up here, and here. And then they move away from each other, and that's what this rarefied part in between those sections are. But you can see that the wave is moving horizontally, but the oscillations are also horizontal. Sound waves work this way. So when you speak, for instance, you're creating pressure differences whose oscillations move towards the person you're speaking to, rather than vertically or perpendicular to that motion. So that's longitudinal. All right. Also, we learned the characteristics that are important for waves: frequency, wavelength, speed, amplitude. These are the big important characteristics of a wave. Okay? If you know these characteristics, and in fact you really only need 3 of them, then you know everything you need to know about the wave. And in fact, mathematically speaking, we can write down a function which represents the wave, all the characteristics of the wave, and from which we can learn all the information we need about that wave, and that goes like this. Let's say the height of a wave at some time, and actually we'll do it the fancy way, and some position. So for instance, if we have a wave like this, and I say, okay, I want to know at this location, at time t equals to 3 seconds, where will the wave be? How high will the wave be? And it'll be right there, of course. And so that'll be the height of the wave at this time, at this position. It's equal to, depending on how you want to write it, but I'll write it like this, the easy way, a, some number, and this number tells you about the maximum amplitude, so how high the wave can possibly get, times the sine of kx minus omega t. Okay. K is what's called the wave number, and it's equal to 2 pi over the wavelength, lambda. And omega is called the angular frequency, and it's equal to 2 pi times f, which is the linear frequency. Now, the x and the t, a lot of people get this confused. These are just variables, x and t. This is, as I said, if you want to predict how high a wave will be, you have to feed this equation. What time are you talking about? That's the t. And what position, so where at in the ocean are you describing, for instance, or a lake. If we're talking about a lake, you throw a rock into the lake, that creates a wave flowing through the lake. So you have to tell me, okay, where on the lake do you want to answer this question? That's the x. What time are you talking about? Did you already throw the rock? Has it been 2 seconds? Has it been 5 seconds? How long are we waiting? That's what the x and t represent. That's something you plug into the equation to get an answer out of. The k and the omega, those are the characteristics of the wave itself. The k is related to wavelength. Omega is related to frequency. And then, as I said, A is the maximum amplitude. How high is the highest part of the wave possible? Okay, so this is the big wave equation from which we can determine all sorts of stuff. The last thing we can figure out, the speed, the velocity of a wave is given by frequency times lambda. Okay. Now, we could also write this in terms of k and omega if we wanted. And so we would write, let's see, it would be omega over k. Okay. So that's how you could determine the speed. When you look at this wave equation, there's a k sitting there, there's an omega sitting there. There'd be numbers. You take those numbers, and you could solve for the velocity. So this equation tells us everything. It could tell us the amplitude, it could tell us the wavelength, it could tell us the frequency, and from those also it can tell us the speed of the wave. So, as I said, this video, what we want to do is do a couple of example problems to see how this works. So let's take an example. For a wave whose frequency is, let's say, 300 hertz, and whose wavelength is 4 millimeters. Write the wave equation assuming the max amplitude is 2 meters. All right. Well, let's see. I know the general wave equation is y equals a sine kx minus omega t. I also know that k is given as 2 pi over lambda, and omega is 2 pi times frequency. So given all of this, let's write down the wave equation with the numbers associated with this problem. Well, first of all, the A I already know is 2 meters, so that's easy. Y equals 2 times the sine of. All right, now I need K. Well, I don't know K from the problem, but I do know the wavelength. The wavelength is 4 millimeters. So since I know lambda is 4 millimeters is 10 to the minus 3 meters. That's lambda, so I could write K as 2 pi over 4 times 10 to the minus 3. So that's our K times X. Now, if you wanted, of course, you could stick this number in your calculator and get a decimal answer for that. That's perfectly fine. But for now, I'll just leave it like this because what's important is how to plug the numbers in appropriately. But as I said, if you're on a test or you're on homework, if you want to plug in 2 pi divided by 4 times 10 to the minus 3 into your calculator to get a number so it looks nicer, go ahead and do it. That's fine. And then minus omega, well, omega is 2 pi times f. I don't know omega, but I do know f. Frequency, hertz, is f, and so it's 300. So this will be omega is 2 pi times 300. So that's my omega times t. And there's my equation. Now again, if I want to go ahead and simplify this, plug the numbers in my calculator to get something that doesn't look all nasty, then what I would do is I would get y equals 2 times sine of 2 pi divided by 4 times 10 to the negative 3 gives me 1570.8 x minus 600 pi is 1884, or actually, when you round it, 1885 times t. Okay. Some people like to leave the pi's as pi's, whatever you want, as long as you give me one of these answers. I have the ability to tell if you're plugging it in the calculator, get a decimal, or if you're leaving the pi's, I'll know. The most important thing is, do you understand from the problem what all these numbers represent and where they go? Frequency, or linear frequency, is f. Angular frequency is omega. The wavelength, that's lambda. For the equation, you need k, which is 2 pi divided by lambda. So that's our first example. Let's try another one. Let's do this one. You are given a wave which travels at 350 meters per second. If the frequency of the wave is 100 hertz. Write the wave equation. Okay. Well, again, wave equation, y is equal to a sine kx minus omega t. This question, I'm not given an amplitude, so I'll just leave it as a. I don't know what a is. A is fine. I need k and I need omega. What am I given? I'm given the velocity is 350 and the linear frequency is 100. But I need k and I need omega. So how do I get these? Well, omega, that's easy. That's 2 pi times f. So 2 pi times 100. I'll leave that as 200 pi. Okay, that's fine. What about k? Well, k, given that I know the velocity, I can get from velocity is omega over k. So I solve this for k, and I get that k is equal to omega divided by v. And for us, our omega is 200 pi, and our velocity is 350. So I stick this in my calculator, 200 over 350 times pi, and I get 1.8. All right, so now I know k is 1.8, omega is 200 pi, so a sine 1.8 times x minus 200 pi times t. So very nice. These questions are not all that complicated as long as you're aware of number one, what are the characteristics, and number two, how they relate to each other. How does k relate to lambda? How does frequency relate to omega? How does velocity relate to those two things? Now, of course, I could have used velocity as frequency times lambda. I could have solved this for lambda to get velocity over frequency, and then say 350 over 100. And that would have given me lambda. And then with lambda, I can get k by saying 2 pi over lambda. That's another way of doing this if I wanted to do it that way. This way, I just decided, since I want omega and k anyway, use the omega and k relationship. But a lot of people remember this version of velocity, and so you could use that one. That's fine. One more quick example. Given the equation y is equal to 10 sine of 100x minus 60t, I want to calculate frequency, wavelength, and velocity. Okay. So I look at my equation. I say, okay, this 10, that's amplitude. I'm not asked about amplitude, so I leave it alone. 100, that 100, the number in front of the x is k, which is 2 pi over lambda. And in the 60, whatever the number in front of the t is, that's my omega. And omega is 2 pi times f. All right, so first I want to calculate frequency. Well, there's frequency sitting over there. So I know omega is 2 pi f. So f must be omega divided by 2 pi, which is 60 in this case, divided by 2 pi, 30 divided by pi. Now, of course, if I want to get the answer, the actual decimal answer, I can do that. That would give me 9.55 hertz. So either one of these numbers is fine. What about lambda? Well, here's lambda with the k. So I have k is 2 pi over lambda, which says lambda then must be 2 pi divided by k. So that for this problem is 2 pi divided by 100, which is pi over 50. And again, if I want the decimal, plug that in my calculator, I would get 0.063 meters. And again, either one of those numbers would be appropriate. Finally, if I want velocity, velocity can either be frequency times lambda, which for our problem, frequency turned out to be let me do it this. Fancy. 30 over pi. And lambda was pi over 50. Pi cancels pi, and so we get 3/5. The other way to do it is with the omega and the k. So velocity is omega divided by k, which for us, omega is 60, k is 100. So the zeros cancel. 6 over 10 is the same as 3 over 5. So you can see either version of the velocity equation works, obviously, or else it wouldn't be the same equation. And so this is good practice. Thankfully, it's not all that complicated. Once you know the pieces of the equation, you just pick them out of the equation, and then you relate them to the things you're trying to find. So I hope this has been helpful to let you see how to use this equation, how to figure out the different characteristics to allow you to work on the homework pretty well. So until next time.